Okay, good morning again. We're going to get started up, and this next session is going to feature work in both our AI and ML domain, but also in our systems, structures, health monitoring technical group. Our first presentation is going to be from Dr. Parisa Shokouhi from our engineering, science, and mechanics department. And she's going to talk about physics-informed machine learning for shear failure prediction from time-lapse ultrasonic data. And you may have seen a little bit of a preview of this from one of the poster sessions yesterday evening from one of Parisa's students. Parisa?
Good morning. My name is Parisa Shokouhi. I am a professor in engineering, science, and mechanics. I'm also a graduate faculty in acoustics graduate program. And my talk today is going to be on physics-informed machine learning for prediction of shear failure from time-lapse ultrasonic data. I'd like to acknowledge the students involved in this particular work. Above, who is sitting here, Rushali has graduated, and Mikhail, who is going to graduate in a few years. Also, my collaborators, Jacques, Riviere, my collaborators from computer science and IST, Lee Giles, Dan Kiefer, and my collaborator from geosciences, Chris Maroon. Before starting to talk about this particular topic, I'd like to tell you a few words about our research group. Let me go back. So this is a word cloud made by one of my students. You see things centered around wave propagation and ultrasonics, but we do a lot of different things. I just happen to extend in different directions. Just to give you a flavor of these different, I should get used to this, directions. Some of our research I would call laboratory scale geophysics. We have projects supported by Department of Energy where we try to simulate geophysical phenomenon at laboratory scale. We have developed sophisticated experimental setups that we can do ultrasonic measurements in the lab under high pressure, high temperature conditions. And we do machine learning and data analytics. I'm asked to talk more about that today, and you're going to see more about that here. We do some work in biomedical ultrasound. What you see is an image of lung. I've also worked on bone fracture healing. A good bunch of my research projects are related to ultrasonic non-destructive evaluation with a focus on nonlinear ultrasonics. You may have met some of my students last night. Some of them were banned from attending the meeting because they got awards the previous year, so they were not presenting. This is the rule of CAV. You may also have seen one of my students presenting on elastodynamic metamaterials. We are using resonant metamaterials to control lamp waves and surface waves. And the last but not the least is our capabilities in simulation and modeling. We have developed models which can simulate ultrasonic and vibrational response of specimens with millimeter size, but heterogeneities in the micron scale, multi-scale modeling. And I'm going to touch upon that a little bit today at the very end. So with that introduction to our lab, let's get started about the topic that Steve wanted me to talk about, and basically the focus on machine learning and data analytics. So beyond the talk that I'm giving today, we are using machine learning in a host of different contexts related to acoustic and ultrasonic data. So I'm going to, at the end, give you a little bit of flavor of what we are using machine learning to solve inverse problems. Basically, how can we interpret ultrasonic data for material characterization? And some of the other things that we are doing, automatic signal classification. This is useful for acoustic and vibration data. We use that in the context of decision making as well. Other topics, actually, the way I started with machine learning was with data fusion. Then I was back in BAM in Germany, and we used that for the data fusion. And also we are doing all sorts of other studies where we are using physics-informed machine learning to solve mechanics problems, and also relating acoustic emission and permeability, again, in the context of geothermal energy in some laboratory and field test setups. So with that introduction, let's actually get to the talk that I like to focus this talk today on. So we want to talk about how to learn from time-lapse ultrasonic data to predict shear failure. To give you a little bit of context, time-lapse ultrasonic data can be used in different contexts across length scales. At the smaller scales, in a structural health monitoring, if you have embedded transducers, you can send pulses and you can monitor the state of the material as your structure is in service. Some of my earlier work is related to that without any machine learning. And then at larger length scales, let's say in geothermal reservoirs, and even for carbon sequestration projects, people use borehole seismic to monitor CO2 leakage. We put the CO2 in the ground. We want to make sure it's not escaping. And if you go to very large scales where people call acoustic seismic, people use active source seismic for monitoring the state of faults with the motivation to predict earthquakes. So this is something that people use across the length scales. What I want to talk to you about today is about a data set where we collected in the laboratory. We use ultrasonic data for monitoring. Let me tell you a little bit about the data first. So the data comes from these sophisticated friction experiments. What makes them very sophisticated and very unique is that we can create the state of stress in the lab. This is being done at Penn State, rock mechanics lab. I collaborate with colleagues in geosciences. What we have added to their setups as acousticians is a very sophisticated system to have arrays of transducers to monitor the processes as different things happen, in this case, friction. So here you see 3 blocks. The middle part is being pushed down at a constant speed to create friction. And at the same time, we are probing these faults using ultrasonic data sent regularly during everything else which is happening. This creates large, huge data sets. We could do the same with acoustic emission, and we do that also. That's not what I'm going to talk about, but I could have had a talk about our work on acoustic emission. So how does the data look like? If you look at shear stress evolution versus time, you see at the end, forget about the beginning, but at the end, you see these really small cycles. These are sticky slip cycles of friction. So you have a sticky slip, and the beauty of these experiments is that through this collaboration with Chris Marone, we can create irregular cycles, and we can create many of them. He knows how. So what we do is we monitor with these real lines, with these blue lines throughout the experiment. We monitor the state, how things are changing. And this is a cartoon. We're sending a lot more pulses than the blue regal lines you see here. I'll show you actually. So if you look here again, this is the experiment, shear stress versus time. If I plot all the signals that we sent in gray, this is actually how it looks like, believe it or not. You kind of see how their amplitude is changing with shear stress. Very cool. Let's zoom in. You see many of them. Each line is a signal, and zoom in again, you see the signal very nicely. What do we do with this data? Typically, what people do, look at the first wave packet. I've colored it in orange, and they create features. We are acousticians, we know wave speed and amplitude is important. For example, in some other studies, we have extracted other features, but for this today, just wave speed and amplitude. How do we do that? We calculate the amplitude in frequency domain. You could also do it in time domain, of course. And wave speed, we use cross correlation to get time shift with respect to a reference, and then we have wave speed versus time. So for each of these friction experiments, we have a history of wave speed and amplitude with time. Putting this all together, on the top is shear stress versus time. Let's look how the amplitude and wave speed change with shear stress. Good news is, if you look at these data, and other people have done that too, you see a systematic change, right? It looks like our features are following shear stress. That means there are some physical reasons to believe that if you input these features, you can predict shear stress. So we are not just shooting in the dark with the data. But these relationships, also you see the systematic variation, the relationships are not trivial. This is the so-called pair plot. If you look at how wave speed and shear stress are related, or how any of these different parameters are related, the relationships are not like a linear, nice curves that you can use. Let me show you a less computer science-y plot. So if you just plot shear stress and wave speed or amplitude, the relationships are complicated. It's variance using, for example, machine learning to go from one to the other. It's complicated, let's use machine learning. And this was our first motivation. So a couple of years ago, the paper is already published in Geophysical Research Letters in 2021. We set out to do exactly that. We said, okay, let's see, these machine learning methods, can they predict shear stress from these features? So the input would be a time series of wave amplitudes and speed. You have different models. We used both machine learning and deep learning models, and then we could predict nicely shear stress. And I'm showing also a slip rate, tau and V. So everything seems to be working fine. We showed that deep learning was better than machine learning. It transfers better, just produces better models. So why I'm talking about physics-informed machine learning today? The fact is, for data-driven models to work super well and to work from going from one domain to the other, you need a lot of data. And not just a lot of data, you need a lot of good data. So the motivation for using physics-informed machine learning is that if you have a lot of data, which is good labeled data, which normally we don't have in scientific applications, you can use just machine learning, deep learning, fine. If you have really good physical models, your system is simple enough to be described well with your physical models, you don't need machine learning. In scientific and engineering problems, we often fall in between. We have some good models, we have some data. So integration of physics and machine learning becomes important when we don't have a lot of labeled data. Also, there are other reasons to think about machine learning. Imagine you have a lot of data, but your data has some systematic errors, some biases that you don't even know about. You develop a model. Why is it a good model? It may not even conform to basic rules of conservation of mass. I don't know, some basic equations in elasticity. So that's a danger. And the last but not the least, you don't want to have a model which works only for one data set and fails to predict on another data set. If you use physics, it looks like it works as an equalizer, because physics is common between different data sets. So it kind of makes your model a little bit worse sometimes, but your model works better if you go from one data set to the other. So I hope that gives you enough reason to listen to the rest of this presentation. So this is why we have started to think, okay, what if we didn't have this very large data set? What if we had less data? Could we use physics to make our models physics informed? There are different ways to embed physics in your model. So one way, very sophisticated, is this inductive biases. You actually design your network such that it mimics a physical phenomenon, and then you work with that particular network. Another way to embed physics is this learning biases, where you explicitly bring the physics into the model. In either case, you cannot use off-the-shelf, Keras libraries. You need to play with the architecture of machine learning. And this is not trivial, but it's doable. We can do it as scientists. We decided to take the second route. So we are changing the cost function to implement some of the basic physical laws. And I have to say that and emphasize it, these physical laws don't have to be perfect. Even if you have some relationships between input and outputs in your model, you may be able to improve your model prediction. So we had data-driven models. We said, okay, let's add some physics. What physics is related to this particular problem? Friction experiments and ultrasound, time-lapse sound. One comes from the friction world, has nothing to do with acousticians. This is an equation that relates the shear stress and the slip rate. They are both outputs of my models, and they show the coupling between the faults and the surrounding medium. But there is this basic equation that I guess most of us have seen at some point, where you look at displacement discontinuity model, you look at the transmission of wave across a discontinuity, here a fault, how the amplitude changes. So we decided to work with these equations. So our physics-informed model basically embeds this equation in the architecture of neural networks. Putting this all together, this is how it looks like. So on the left-hand side, this is the data-driven model. Think about the output as functionals. This is what we had. On the right-hand side, I have these equations. I can add them as regularization terms to the cost function to penalize if the outputs or inputs or their combination deviates from friction laws or basic displacement discontinuity model for ultrasonic transmission. So we considered two different models, one only looking at the first equation and the second looking at all equations. The second equation in the middle is kind of just coupling between the two equations. So that's just a coupling equations. So this is kind of the framework that we started off doing. Remember the motivation I gave you. I said the motivation is to use less training data because we don't have labeled data as scientists. So one thing which is very important in machine learning is how much data you have. So this is our entire data set. These are shear stress cycles for the experiment I'm showing you today. If you have 70% training data, you have 10% validation and 20% testing, color-coded, this is how it looks like. We tried to see how these models perform relative to each other. If we change the training data from 70%, which is a lot, to 5%, which is only 15 cycles, how this is going to change the performance. For what I'm showing you here, I keep the validation and testing the same. Let's look at the results. We look at the performance of these models with R2 squared. If it is close to 1, it's good, close to 0, terrible, and somewhere in between. So when you develop machine learning models, the first thing you have to do is to make sure that they overfit your training data. That means that you actually have a problem that is solvable. So it looks like for all the different training sets going from 70 to 5% on the x-axis, we have good models. I told you in the beginning, it looks like the physics tells us that this should be possible. Validation, this is where the hyperparameter tune things degrade a little bit, but not much. And we evaluate the performance on test data. Let's look at this performance closely inside those boxes. One thing we can see the two brownish color columns are always larger than the gray. So PINN models, form models always outperform the data-driven. That's good sign. The second thing I want you to notice is just look at 5 and 10% training data. You can see that, for example, in the bottom row, the difference becomes more significant. So when we have less data, the physics informed seems to be doing pretty well. So this is interesting. One thing that I forgot actually to mention earlier is that we have some experimental parameters. We have normal stress, we have density. When we gave these equations in, we decided not to tell the model what these parameters are, not to say what the mass density is. Let the network learn it as a kind of a balance and check on our modeling approach. Now let's look at what the model has learned. At the very bottom, these are the experimental parameters. You see, for example, normal stress is 10 megapascal, or you see that the mass density is 2600. Now look at the row 8, I don't know how visible it is. You can see that the PINN model predicts or estimates sigma as 9.8, pretty close. The mass density 2646, pretty close. We haven't given this any of that. We just have given the equations and kept them as learnable parameters. It's working. It even gives us the physical parameters that we have in our experiments. Where are we going with this? We are applying this in different contexts. We have developed this framework. This is not trivial. And I saw that there are some interests in the group in the previous presentation. So talk to me. I'm happy to talk to you more about how they apply this in other contexts. We are using this for acoustic emission now, where we have a lot of data, and I think we can learn a lot from the data. But I would like to have the physics as a part of that. If there is time, do I still have a few minutes? I like to show you a little bit about some other work that we do with machine learning, which could also set the stage for the next talk. And that is inverse problem solving to learn from ultrasonic investigation. We do a lot of non-destructive evaluation and health monitoring, specifically now for additively manufactured metals, but for a lot of other materials also. So I'd like to show you a little bit of our work there if there is any interest or collaboration opportunities. So the basic problem is this. We want to know about the macrostructure of materials. For example, in the simplest case that I'm going to show you here, we want to know about macropores. How much do we have? How big they are? We send in a pulse, we get a response. So the question is, from the response, what can we say about the macrostructure? This is an inverse problem. We have physics-based solutions for that, but can we use machine learning to ease our inverse problem solutions, which are normally very computationally expensive and difficult to do? So that's kind of our motivation. How did we start to go about this? We started with numerical simulations. So we developed models where the specimens can be millimeter size, like tens of millimeter, but the heterogeneities can be microns, tens of microns, for actually starting from 5. And we were able to simulate ultrasonic and vibration data, and we were able to verify them. Once we validated and verified, we created a database. So we created the database. The question was, can we use machine learning to learn about the porosity parameters that we use to create these models? This is kind of how the problem is set up. If you want to see the data set that I'm going to show you here, we have several levels of porosity and several levels of mean pore diameters or radius here. So we created a database. Now we have a lot more databases, but this is the results that I'm showing you here. So we wanted to see if we can get anything good out of it. We applied machine learning and deep learning. So random forest and XGBoost, both are tree-based methods. Here, we are not using any physics features as input. We are just inputting the signal as a whole. And we look to see whether we can retrieve the porosity and porosity size. The confusion matrices are shown below. You see that the accuracy is pretty high. We also used deep learning, convolutional neural networks, and NLP models, and we see good accuracy. So it gives us a lot of confidence that this idea is feasible. So where we are going with this? But this is simulated data. In fact, using simulated data for machine learning is a weak way of implementing physics also in machine learning. It's different from what I showed you before, but it's a way to have physics in the machine learning framework that we have. What we are doing now is we are implementing these models together with the experimental data, both ultrasonic signals, also images using phase arrays. Again, the question is whether we can capture the macrostructure, we can image it from the input signals without going through inversion, the classical inversion. So this is kind of where we are going, and we should have a few papers out in the next few months. So with that, I can conclude my talk. I hope that I gave you a flavor of some of the work we are doing in physics-informed machine learning, how we are implementing that for shear failure prediction in friction experiment, the one that I showed you. In our work, we show that physics-informed machine learning is giving better results than data-driven models, improved prediction, and we see that for small data sets, we can get good accuracy. And I also showed you a little bit about our work on characterization, ultrasonic characterization, and solving the inverse problems. With that, I thank you for being here. I cannot stay very long. I'm actually on an NSF panel at the same time. So, but I'm happy to talk to you more if you are interested in any of the things we do in our lab. Thank you very much.
Okay, next we have Dr. Jay Keist, who's going to be talking about additive manufacturing process. Thank you, Jay.
So yeah, my name is Jacques Keist, and I'm an assistant research professor at the Applied Research Laboratory here at Penn State. I'm also affiliated with Sim3D, and the goal, this short presentation, but the goal is to kind of give you an introduction to Sim3D and the additive manufacturing that we're doing here on campus, as well as just going into the background of a little bit of additive manufacturing, some issues that we see in terms of getting this qualified and certified for actual applications, and as well as discussing defects. There we go. I'm not going to go into this. I'm sure that's already presented here, but I am a research professor in ARL. My group within ARL is materials engineering evaluation. We do research that is on more of the process, understanding process, how to impact structure of a metal or ceramic material, and then how to impact the final properties and performance of that part. So this is examples of the qualifying for AM. This is picture of the first Navy part, NavAir part that was flown. It was a replacement program with additive manufacturing. My background was in characterization. I'm affiliated with the material science department here on campus. So we do characterization in our group, and we also do non-destructive testing, but with the emphasis on eddy current and X-ray and X-ray CT systems. And we do a lot of work with repair as well. To give an overview of the SEM3D, this is the Center for Innovation Materials Processing through Direct Digital Deposition. I like to think of it as an umbrella organization within Penn State. It is directed and run by the Applied Research Lab, but it is co-directed by the College of Engineering and the College of Earth and Mineral Science. It was initiated from a DARPA as a national resource for additive manufacturing over 10 years ago. And we've been operating ever since. This picture here just kind of gives us a sense. We try to think of ourselves as bridging the basic science all the way up to the applied. So getting the additive manufacturing actually used systems. This overviews a lot of the equipment that we have around Penn State. SEM3D is where most of these equipment are. It's located at Innovation Park. You're more than welcome to inquire about visiting. But this gives them information of like all of the systems we have. We have 3 bed systems. We have several directed energy deposition systems, and we have binder jet systems.
Oh, we got the banana. I forgot that.
And this is an example. If you are unfamiliar with additive manufacturing, most of the processes are a layer by layer process where you're depositing, infusing your material, and developing, and from that, it gives you the ability to develop and produce fairly complicated geometries. This is an example on the upper right is a, let me see if I get it, no laser pointer, but yeah, right there. Upper right is topological optimization, where you're taking in your stress state for a particular bracket in this case, and then you're allowing the computer program to understand how it can reduce weight as much as possible. And then we can actually print that within the additive manufacturing systems. This is a heat exchanger. This is an example of design for additive manufacturing where you're taking a complicated P-bar housing but with several parts, having to have gaskets, and you can make it all within one component within additive manufacturing. This is a replacement program. This is with a program we did with Army. A lot of these helicopter systems are over 30 years old. They don't know where or how they can get replacement castings because their OEMs may be gone. So this is again trying to use additive manufacturing for replacement of a fuel elbow right here. This is a sub-rescue manifold, again showing how complicated geometries we can get in there to help reduce weight for this manifold. And then finally, this is a DOE project we had with low flow turbine and for power generation. And again, showing you can get some complicated structures in there to reduce weight and actually fine tune your prod as needed, fine tune your fins as needed. This just gives an overview of what we're trying to do as we're trying to bridge everything from modeling, characterization, institute monitoring of the process, and also data collection, data management. There's a lot of things that can go on here that we're trying to bridge over as far as what we're in as our footprint. Some areas that I'm directly involved with, particularly on the metal IAM side, is developing process developments where we're understanding how the process impacts the structure, how we can manipulate that to change the properties as needed. Another thing that we've been doing is tailoring properties. This is an example in the middle here of a grading for aluminum alloy where we're actively changing the thermal expansion coefficient. This is for gasket space applications for this particular component where we are trying to use this coupling between a aluminum and titanium component within space. Titanium has a very drastic, very different thermal expansion than aluminum. So we're using this composite and what they call sometimes a functionally graded material to make a gasket in this case, so we could bridge those two materials. Another thing we do quite a bit at SEM3D is qualifying. These are two examples that we did for NavAir and one for Army. The idea is that both of these are for replacement parts, but how do you qualify these? You need to make sure that each of these components that you're making are able to perform as expected. So this is another thing we've done as well. So now going into kind of the issues that we're dealing with. Over here, this is something I put together, now it's about 5 years ago, of just what are some mechanical properties that you can get from additive manufacturing. In this case, it's the titanium alloy Ti64 that's produced by additive manufacturing. If you look at the literature, you can see a wide range of tensile strengths and a wide range of ductility elongation values. So if you are a design engineer, and you're looking at additive as a method to make your component, you look through the literature, you may really wonder, what can I expect from this as far as my performance? And so what we're realizing, or we have realized, is that, really this area is tied to how you're processing your components. And this is an example for titanium, where if you're increasing the amount of heat that you're using when you're building your components, you're changing that structure. And that structure is directly impacting your properties. So it's critical to understand how that impacts your process, so that if you, for instance, if you're running into a condition like, hey, I need to make sure I'm getting my tensile strengths above 1,000 megapascals, and I'm getting my elongation above 12%, you need to understand how you need to get that process under control for you to do that. And that brings up another important thing that comes up in additive, and that's defects. A lot of these processes are, they're time consuming. This upper right is a powder bed fusion. You're doing a layer by layer process, typically 30 microns by layer. It may take 10 minutes to do that 30 micron layer. Imagine you're building a part that's over 100 millimeters in height. It could take weeks to build that part within a powder bed system. In that time of weeks that you're building, a lot of things can happen, and defects and so forth. And this is another thing that another popular way of building parts is what they call direct energy deposition. Again, it's layer by layer. In this case, you're directing that melt pool around the build block, and so you can make your component. But again, a lot of things can come up. The powder may get clogged, for instance. You may end up with defects. So what does that result with? This is an example of a fatigue craft. What I'm doing here is I just took literature data, again, for titanium alloy. And I took the max stress that they did the fatigue cycle and versus how much cycles it was able to obtain before failure. Just for reference, Ti64, they determined the fatigue limit is around 600 megapascals. So a lot of additive manufacturers are able, in this blue region, is able to achieve that 600 megapascal fatigue limit, but a lot of it was not from the literature. And probably what's causing, the issue is defects that are causing some significant failure in these processes. So I keep on choosing the wrong one. And that just goes through the literature that are used for this. So what is it? There's a lot of basic defects that we find in additive manufacturing. The main ones are the top three is lack of fusion. Lack of fusion example here shows what you're basically doing when you're building your layer in a fusion process where you're melting. You may not have enough power, and you end up with an area that didn't fuse. And this is a case that a failed component that had a lack of fusion defect right here. Another thing is keyhole collapse is an example of what happens is that when you run high powers, you can develop a keyhole condition, which is basically a deep trench of a melt pool. And if you're not careful, that melt pool can collapse in creating a pore. As it solidifies, metal wants to shrink, and that pore forms in that area. Another thing is gas porosity. If you get impurities, like anything on the metal powder or the metal wire, things like oil and grease, that is going to burn up and cause a gas pour. And there's an example of a gas pour here. Finally, we can get some solidification cracking. Certain alloys do not want to be melted, or they do melt. They can form cracking during solidification as metal tends to shrink. And therefore, if you don't have enough metal to fill in those shrinking areas or voids, you can end up with some cracks like this. And then finally, additive manufacturing can build a lot of stresses, and that can cause solid state cracking. And this is an extreme example here where we had a build plate actually crack directly off the plate just by building this. And that's another area that we're very concerned about. There's other things like surface connected porosity that has to do with the additive manufacturing process. You can get around that by just machining your surfaces as needed. And finally, impurities can find their way in as well. We have a large program at Sim3D dealing with censoring and trying to do in-situ censoring during the build. And this is an example of a powder bed process, which I told you it may take weeks at a time to do your building. We've added things like high resolution cameras, coaxial cameras, high frame rate cameras. We've done things with optical process emissions where we're doing spectroscopy on the, where you're looking at the spectroscopy that's coming off the laser interaction with the melt pool. And then we also do things with like adding acoustic sensors. In this case, we're looking for, as I mentioned, the cracking that I showed before, understanding of how that cracking occurs and seeing if we need to stop the process with those acoustic sensors. We've done some work with also with thermal imaging and melt pool sensors, and also a laser profilometry to understand the laser height as well. And so what do you do with this data? Well, you can get over terabytes of data from one of these builds, and then that really becomes an issue with how do you understand all this data and do some type of analysis of it. This is a work by Jan Petrick at ARL with help of Steve Corbin and old student Zach Snow and my colleague Ted Rutzow of using neural network processes to help predict issues or defects within the build. So in this case, these are a small cylinders, roughly 12 millimeters in diameter that we built. This is a slice that we did afterwards by X-ray CT. And we noticed that we had some flaws. These are small little pores that came up during the AM process that we see here. When we go back to the neural network, and we can actually predict those areas by taking these acoustic spectral data, the scan vector modifications. This is following the laser path, and also doing a camera, just a simple camera, flash camera, and using that data and doing a neural network prediction of areas that are of concern. We can find out that we can map these areas pretty well from one area to the next in terms of predicting areas that may be of concern for the pores. The next question is, can we actually bring these in-situ data to actually try to correct these as well? Right now, we feel confident that we can find areas of problems that may be good in the build, but the next step, of course, we want to actually actively repair these. And I'll just finish here and finalize is going through the fact that we've been in Sim3D has been around for almost 12 years. I've been here almost 8 years. And we've got, as far as additive within other research organizations and well around the country, Sim3D and Penn State is probably one of the lead research institutions. And this is just an example of the peer-reviewed journal articles that we got out per year up to 2019. I need to update this slide. So with that, I'll finish and open up to any quick questions. Thank you.
I was very interested in the plot of the stress versus cycles. Can you go to that slide?
Yeah.
So do you find, it's hard to read the graph, but if you have a material that's bilinear like steel, like under a certain pressure or under a certain stress, you can have an infinite number of cycles and it won't break. You find that that's true with additive materials that are similar?
I have not done enough fatigue testing on steels to say that yes, there's a fatigue limit that that we have seen that doesn't break. I would say 80% of the fatigue that you see is in titanium and nickel-based alloys. But what I've seen is I think we are comparable to conventional wrought-based products, but there are still issues that on steels that we're I wouldn't be able to answer that at this time. Is there a real fatigue limit that we don't have to worry about it ever breaking?
Are you developing like a different SN coefficient for these materials, or are you assuming that it's the same behavior?
We're assuming the same behavior to what we're trying to do. For instance, I'll go back, the one process, how far do I need to go? This particular one, that's an example. We compared ourselves directly to the rot component. So we had to do the same testing that they had to do to qualify their rot machine component. We did that for the additive. In this case, for the titanium, we were able to, we were in parity and slightly above for fatigue results for this particular process. But titanium is really good. It works pretty well with additive. Some areas they may not work very well. Things that are dealing with that may have issues with the since we're building with a powder, a lot of contaminants can get on that powder. Some metal alloys, it's a little bit more difficult to work with additive because of that.
Thank you.
Mm-hmm. Thank you.
Are the talks on the desktop? All right, perfect. All right, thank you all for being here. I'm Chris Kube. I'm an assistant professor in engineering science and mechanics. So Jay transitioned this pretty nicely for me. I'll be talking more about ultrasonics in relation to the microstructure and the melt pools that we see in AM processes. So linking ultrasound to the fundamental things that happen that material scientists and people doing advanced manufacturing are interested in. So this is a picture of a melt pool. So this is a cross section of a melt pool that you see in powder bed fusion that was taken with X-ray radiography, for which we're monitoring these things with ultrasound. So there's going to be two different themes here. Oh, the clicker. Yes. Okay, two different themes here. So one's going to be more ultrasound integrated into a real process, monitoring, potentially monitoring the microstructure of the part as it's being printed. The other is the melt pool monitoring. And the advantage of ultrasound is that it senses the internal volume of the structure. So Jay put out several sensing modalities that are primarily sensitive to the topmost layer. So you can see the topmost vantage point of the melt pool, but you can't see underneath of it. So this opens up the door to answer a number of provocative questions and potentially providing answers for these. So these first three are for the in-process part monitoring. So can you use ultrasound to monitor or measure average grain size? Can you get information about the phases present, residual stress? And then on the melt pool side, can you sense process defects that form? So the porosity that Jay was mentioning, melt pool dynamics, melt pool dimension and shape, solidification rates, all of this is beneath the surface, right? Solidification, cracking, pore formation, microstructure formation, and so on and so on. Can we eventually use this to determine this process window? Process window refers to, can we know the power and speeds it takes to print a part of high quality? So getting ahead of the traditional NDE, where traditional NDE is saying this part's good, this part's bad. So working with the material scientists ahead of time. And much larger picture, can you use a traditional ultrasonic NDE technique, ultrasound, to bring together these communities to make these very large advances? So we started down this path about 5 years ago with APS, where I teamed up with these experts that do high-speed X-ray radiography. and we synchronize the ultrasound with the X-ray. So we have this ground truth. And we have all these other various collaborators that have expressed interest that we're collaborating with. And then I want to highlight Lawrence Livermore, who's supporting the next melt pool measurements at Argonne later this November. So something's still to come. So I'll be talking about two configurations. The first configuration is for the melt pool monitoring. And so this is set up specific for synchrotron measurements. So here we have the yellow beam that depicts the X-ray that's imaging the cross section of the melt pool. We have the red laser actually creating the melt pool. And then we have these ultrasonic immersion transducers that focus the ultrasonic energy right where the melt pool is, that senses the melt pool dynamics. So that's configuration one. The other is ultrasound within the process. You can see several ultrasonic transducers that are integrated into this redesigned build substrate in an EOS M280. It's a powder bed fusion system. And we're using ultrasound to monitor what's going on in these different parts as they're being built. And significance to this, this is the first instance that ultrasound has been employed to monitor several parts simultaneously. So we could potentially see differences between the parts or do process parameter, looking at different process parameter spaces for these different parts to say that we have the expected microstructure, we don't, and so forth. So basic principles behind the technique. We all know that, being acoustics, we all know that when you have an incident wave at an interface that separates two medium of different density or stiffness, we have part of that wave being reflected, part of it being transmitted. And so then in the application, if we look at this part, if we have a crack that forms at the part, there's a definite acoustic impedance difference there. So we're going to get a reflection from that. In this case, if we have pretty good fusion at the build insert part interface, it might be microstructure that causes that impedance difference that we can sense. For the melt pool case, we're thinking about impedance differences. So when you're melting, you're creating a liquid region. So this red curve represents the liquid solid boundary. We get scattering of ultrasound from that boundary, and that scattering tracks with your melt pool behavior. So I'll be mainly highlighting time of flight measurements in this talk. So just to get everyone calibrated on the same page, I like using this analogy where you've probably done this before, trying to figure out how far a lightning strike is away from you. So you see a lightning strike, that light is almost instantaneous to your eye, and then the acoustic wave comes a little bit later. And so you note the time it takes to arrive from t equals 0, so you're counting in seconds. You take that time, multiply it by the wave speed in air, 340 meters per second or so, and then you can get the distance that that lightning strike is away from you. And then if the storm is moving closer to you, that thunder takes less time to reach your ear. And so I showed three signals on the right-hand side. If we put our, if we're imaginative, we can plot this. So we have these three signals. Each of these vertical slices is your time amplitude. And you can plot this as the arrival time of the thunder. So that's the time you're counting. And maybe the origin is at the first lightning strike that you saw. And then the x-axis becomes the storm getting closer. This might take minutes. So how does this relate to our additive manufacturing? For the melt pool side, the vertical axis here is the arrival time of ultrasound. That melt pool gets closer to your sensor, it decreases. So you see a decrease in the arrival time, and that corresponds with the melt pool getting closer. For the part monitoring, we get reflections from the topmost layer of the part. So this might look like the very first signal that we collect, and then we add a layer, we get another signal, and so forth. So what would a defect look like? So if you have delamination at one of the layers, we're going to get a reflection from that part, and some of it will be transmitted through to the top surface. So it might look something like this. So I'm going to show results that are somewhat similar to this in a little bit. So the first thing I'm going to look at is this configuration. So multiple contact transducers that we're monitoring several parts simultaneously. And these were the power and speeds that we use. I'm going to only show results from samples 4 and 6 in this case. And you can see that there's different energy densities going into the part. So that means that potentially different microstructures that form, different defects that form, and so forth. And these are the part parameters. So during these measurements, we actually did 3 different stages. So we collected measurements when the laser was active on each of the parts. So looking for melt pool signatures. We're collecting measurements prior to recoating, so without a layer of powder on top of the part, and then when we had a layer of powder on top of the part. So all these measurements, we're left with about 2 terabytes of ultrasound data that we're still going through, which is part of the reason why we're focusing today's results just on samples 4 and 6. So results on these. Sample 4, this is exactly what we expect. So the part's growing in height. So this is a reflection from the top surface, and it's pretty uniform. We expect this to be a nice part that doesn't have a lot of inhomogeneity. And then we look at sample 6. We measured the density. This was 99.92% dense relative to the rot. And then we looked at sample 6 and we saw something really interesting. We saw a constant time of arrival in addition to some energy actually getting through. And so this traces with the top layer of the part, and this stays constant throughout the build. And so this is an indication of some sort of a delamination. And again, this part, even though we saw this, was 99.16% dense. So it's still a pretty dense part. And what's going on here is we get this different impedance at the insert part interface that causes that reflection due to defects that form. So the other part of this, we're going to be looking at melt pool monitoring. So we're using this ultrasound in a pitch catch configuration, so 1 transmitter, 1 receiver, and we're looking at the scattering from the melt pool boundary. So we synchronize everything with the X-ray. So we have a picture of the X-ray image that corresponds to exactly with the recorded signal at that instant. And so we're collecting at about 29 kilohertz or 29 ultrasound waveforms per millisecond, so pretty fast. So results for this is a video. Oh, you guys weren't ready for this. Can you push play on the video? So this is a single point melt pool on aluminum. And so on the left-hand side, you're going to see the X-ray video. So each of these frames is the current snapshot. We have a conduction stable melt pool at this point. The laser's on. The laser's going to be on for about 5 milliseconds. There's a nice melt pool, and then you get a keyhole. So the laser energy drives the material down. It boils some of the liquid metal out of there, and then you get the solidification. So on the ultrasound response, each of these vertical time amplitude is the signal reflecting from the particular frame that was present over here. So if you look at this, this is the point where the laser turned on. This is the stable melt pool. This is the growth of the keyhole. This is the solidification, and this is cooling here. So there's tons of information encoded into this that we're using to back out, fundamental information about your melt pool solidification, microstructure, and so forth. One of the things we did was simply traced the time of flight or the arrival time of the first echo, and we compared that to the melt pool depth that we obtained from the X-ray images. And so we get a very strong correlation between the melt pool depth and the time of flight, including some of the dynamic information that's happening. So how that keyhole is fluctuating in time. Then obviously we have solidification information. So the sort of solidification rate here on the order of about 1 millisecond. So for future work, right on time, we're starting to use fluid dynamics software to actually simulate the melt pools. And we're also connecting the simulated melt pools with wave propagation simulations. And Kelly, do you mind playing the right side video? And so on the right side, this is a frame taken out of the melt pool simulation where we're propagating ultrasound up into it, and we're going to get scattering from the solid liquid boundary and also the vapor liquid boundary here. There's also an interesting effect right where you expect the melt pool boundary to be. We get ultrasound to localize in those positions. And you think about that, you have a gradient in your stiffness and density in that region as your solid is phase transitioning into your liquid phase. So we're interested in the future to explore this a little bit more in our next set of measurements at APS. And that's all I have for you today. Thank you.
Okay, thank you to our speakers. As you can see, there's a large intersection of work between that's going on between our machine learning groups and our systems and structures health management working groups. We have two more presentations before lunch here. I'm going to give you a quick update on some things happening in our systems and structures health management group. And then we have one final special topic presentation by Dr. Jacques Riviere about ultrasound for geosciences. And you saw his name referred to in some of Parisa's projects that are ongoing. They have a joint working group themselves. So I want to just give you a quick update on the System and Structures Health Management Technical Group. The goal here is to develop new methodologies and technologies for managing the life cycle of systems and structures. I thought about creating a word cloud. Parisa beat me to it, so I'll just go with kind of an old-fashioned highlight some of the key themes in the work that we're doing. And that is, we're looking at things like material state awareness, health and usage monitoring, condition-based maintenance, with applications to things like logistics, useful life prediction, and other things that you've seen in the presentations today. So some of the goals of this work broadly are for things like maximizing safety, minimizing life cycle cost, and increasing the capability. And this requires a broad range of engineering areas, actually, things like sensor systems, signal processing, pattern recognition, reasoning, modeling, and damage progression to failure. So the reasoning techniques and the modeling are some of the key things that you've seen examples of today, where we're trying to apply machine learning. It's still primarily, in my own opinion, more on the machine learning side than the AI side. We still aren't, I don't think, leveraging a lot of the intelligence and reasoning tools that are coming online from the AI community that we see in things like self-driving cars and autonomous systems to fit into our condition monitoring and our logistics decision making. But that's coming. Large number of people affiliated with the Systems and Structures Health Monitoring Group. These are all available on the website. So if you go to the CAB website and you look under our group, you'll see a lot of the different collaborators here. And you've heard from quite a few of them today. Again, I encourage you to go to the CAB website and look at the annual report. Each of the working groups has highlighted a number of projects in the annual report, and you can get a little more detail on those that weren't presented today or yesterday. So within, you already heard from Chris today, one of the projects that's highlighted in the report is a project of his looking at residual stress influence on free vibrations. Dr. Andrea Arguelles, computational modeling of vertical crack scattering, another project from her group along with Dr. Susan Trollier-McKinstry, acoustic characterization of cold sintered components. Cliff Lissenden, who is my co-chair for the Systems and Structures Health Management Group, along with Ted Roitzel, nonlinear laser ultrasonics for reduced variability in additive manufacturing. Another with Cliff and an ARL colleague, Abdallah Nasser, mixing elastic waves for non-destructive characterization of microstructure, again, during additive manufacturing. And you can see another paper by Cliff and Parisa and some colleagues at Penn State Hershey using ultrasonic guided waves to evaluate fragility fractures. So Parisa made reference to that in her presentation earlier about her work with using ultrasound for diagnostic imaging in bones. Cliff is continuing to do a lot of work in ultrasonic guided waves for NDE. And then you'll hear a little bit about this, I think, from Jacques on work on mechanistic feedback in the geosciences areas. And then the last couple of papers that are highlighted in the report, ultrasonic measurement of additively manufactured materials, some work that Parisa is doing, and other projects he's doing with Mary Frecker and Cliff Lissenden on metasurface to control surface wave propagation. If you looked at the student presentations last night, there was one where they were using metamaterials, tuned periodic structures to try to dissipate surface waves for seismic effects. And then some work that colleagues of mine and I are working on at Penn State. These are some things that we presented in the past, but they're just some updates on the projects for machine tool and bearing failure analysis. One of the things that we've done there in the last year is started to apply some more machine learning techniques, and so as opposed to purely physics-based signal processing like we were doing before. And then some work where we're looking at evaluating some new MEMS sensor technologies, pushing those to higher frequencies than we've seen in the past with those commercially available sensors. With that, I'd like to turn it over to Dr. Riviere to talk to you about applications of ultrasound in the geosciences. And following his talk, we will have lunch over in the Alumni Hall, same place as yesterday. So, okay, it's just the slides, laser pointer. Okay, thank you. Hello, everyone.
My name is Jacques Riviere. I'm an assistant professor in engineering science and mechanics. I am also affiliated with a graduate program in acoustics. And I work with Parisa, who presented just earlier today, Chris Maron, Derek Ellsworth at Penn State in geoscience and in energy and mineral engineering. And also my former postdoc advisor, Paul Johnson at Los Alamos National Lab, and Robert Geyer. Okay, I've been tasked with giving an overview of why do we use ultrasound for geophysical applications. So I'm kind of the first half of my talk will be about a general overview of why do we do this work. And then I'm going to dive into one of the most recent research area that we have been focusing on. And this is the work by my PhD student, Lynn Gao here. Right, so one of the main reasons in general that we study the nonlinear elastic response of materials is that we can, typically the nonlinear elastic response changes early on if you damage a material. So this is an example of a material that is being fatigued. And if we measure some nonlinear and some linear parameters, the nonlinear, oops, I went too fast. The nonlinear parameters are increasing much earlier than the linear parameters in green here. So if we're able to figure out that something is going on early on, we can take some preventive measures. So that's in the context of non-destructive evaluation. We are interested in the non-elastic response in general for material characterization. So there was a lot of example given earlier today. So this is just to give you an idea of what we measure in rocks and So like we have like 3 rocks here and a concrete sample, mortar sample. And those are the nonlinear elastic response that we measure at the bottom. So you see those shapes are very different. So one of the big long-term goal of our research is trying to infer, like when we measure this, what does it mean about the microstructure that we're measuring? And doing nonlinear elastic measurements in rocks and granular media is great because the nonlinear elastic response is typically very large. So it's easy to measure in some ways. All right, so now why do we care about the nonlinear elasticity in the context of geophysics? So one topic of great interest is to try to relate the nonlinear elasticity with the transport properties. So permeability change in, for example. So this is just an example here. This is the San Andreas Fault in California. And this is the changes in permeability over time. So this is permeability over time. And what we see is that whenever there is an earthquake, so the earthquakes are given by the dashed lines here. Whenever there is an earthquake, the permeability is increasing, and then it kind of drops back down. So whenever there is an earthquake, it's easier for water to flow in the subsurface. And then at the same time, if we monitor the wave speed of the subsurface, we see that whenever there is an earthquake, what we measure here is the, I don't see the pointer. Oh, I'm hiding it, I think. Right, so we see a change in the wave speed. So when it goes up here, the axis is inverted, so the velocity drops. So whenever there is an earthquake, the medium becomes softer a little bit, and then it recovers back to the initial value or not if there is permanent damage. And so if the system was linear elastic, you would get a constant elastic modulus, and therefore you should expect a constant elastic wave speed, right? So the wave speed shouldn't change over time if the system was linear elastic. So all these changes in wave speed are related one way or another to the nonlinear elastic properties of materials. So we are trying to relate these two. Like one idea would be that if you could use seismic waves to try to infer the permeability inside your reservoir. So this is like for earthquakes in general, but this has this is of great interest in the context of oil and gas or geothermal energy. When, for example, the reservoir efficiency will be related to the permeability of the reservoir. So typically what people do in geothermal reservoir was, for example, to pump water down, and if you pump the water down, you try to open up all those cracks in the subsurface to increase the heat exchange with the fluid. So if we can infer the transport properties using changes in elastic wave speed, that would be of great interest. So we do experiments in the lab scale to try to relate those two things. All right. Another area of interest is the phenomena of dynamic triggering of earthquakes. So what happens is if you have a large earthquake, you have some waves radiating out, and the waves may be of large enough amplitudes that it's going to disturb the medium far away from when the earthquake happened. So basically, you have an earthquake that is going to trigger another earthquake very far away. So you may have heard of like aftershocks. So aftershocks, they typically happen right next to where the first earthquake happened. So here I'm talking about an earthquake that happens very far away. So this is an example in New Zealand. So there's a magnitude 7.8 earthquake. This is the green vertical line. And then this triggered a slow earthquake, which is measured using the GPS stations. So you see that and it happens over, this is a slow earthquake. So it doesn't really radiate waves as much. It slips over 10 days. And this was like several hundreds of kilometers away. And so what is happening here, you have a large earthquake with a large amplitude wave. And the wave is large enough that it's going to disturb the crust far away. So if you have a fault that is critically stressed far away, it's going to it's going to slide and produce an earthquake. And in that case, it is a slow earthquakes. This is another example. So this is the seismicity measured off the coast of British Columbia in a few hours after a large earthquakes in Alaska. So again, many miles away. So this is 2002 Denali earthquake. And then another example is this is some tremor measured after a large earthquake in Chile. So the earthquake happened in Chile in 2011. The wave is propagating out all the way to Mexico, and then they noticed that there is some seismic activity being measured by the earthquake in Chile, so very far away. So all of this is because the waves are large enough. We are in the nonlinear elastic regime, and it's disturbing the crust at some level and producing some seismicity far away. Okay, I keep pushing the wrong arrow. Okay, so I showed that plot. Sorry, this one here on the left. So whenever there is an earthquake, the wave speed drops and then recovers. When we do this in the lab, what we are looking at, this is the same setup that Parisa showed. So we have a double direct shear apparatus, and we shear, we push this block of granite down, and then we use a transmitter and a receiver to probe the changes in elastic wave speed. And so we see multiple shear failures, so we call them lab earthquakes. And then in red, what we see here is a change in time of flight. So that's equivalent to the change in velocity. And so we see that the time of flight is increasing, so it's a drop in velocity. But what we see in the lab is that the time of flight starts to increase before it reaches failure. So this is kind of a precursor to the earthquake. So if we want to understand precursory changes to laboratory earthquakes, we are very much interested in this area when the time of flight starts to increase, or when the velocity starts to decrease. And we have noticed that this period of time, like so basically the duration of that red, the length of that double arrow, green arrow, depends also on the nonlinear elastic properties of the bulk of granite. So the nonlinear elastic effect in the bulk are important. All right, so this was kind of the overview about why we are interested in nonlinear elastic effects in geophysics. And so now I'm going to talk about some more recent results in particular. So to give you some background, so for a linear system, we have a linear relation between stress and strain, and therefore the elastic modulus is a constant. And if we send a wave at frequency f inside a medium, we just get frequency f as an output. If there is some nonlinearity between stress and strain to the first order, we are going to get a modulus that depends on the strain, and the slope is given by this parameter beta. If we send a wave at frequency f, we get a wave at frequency f on the output plus a second harmonic to first order that will evolve with the square of the fundamental. And then we have different flavors of nonlinearity. So I'm just using this as a framework for what comes next. So if we have a cubic relation, here we are going to get a curvature for the modulus, and we are going to get a third harmonic that increases with the cube of the fundamental. And then we often refer to these types of nonlinearity as a classical nonlinearity. And this is to make the difference between some more fancy looking stress-strain relations. So if we have any stresses in the stress-strain relation, we get this bow tie for the modulus. And then we also, we get odd harmonics, but then the scaling is different. Okay, so we have different flavors. We call this guy the hysteretic or non-classical nonlinearity. So one thing that we could do is to send waves inside a rock sample and measure the amount of harmonics. What type of harmonics? How do they evolve with? How do they grow with the amplitude of the fundamental? So that would be this thing here. But what we have been using most recently is basically to try to measure in the lab changes in modulus as a function of strain directly. So if we are able to measure this directly, then that gives us much more information about the physical mechanisms at the micro scale. And so this is an example of what we're able to do. So we are able to measure the change in velocity as a function of strain here. And the changes in velocity are proportional to the change in elastic modulus. And we do this using a technique called dynamic acoustoelasticity. So it's a pump probe method. We have a low frequency, large amplitude vibration that, and for that particular example, we resonate the sample on the first compressional mode. And we oscillate at a large amplitude enough that we are going to disturb the elastic state of the sample. And then at the same time, we use a pair of ultrasonic transducers at high frequency. We send like tiny pulses to monitor the elastic state of the sample. Well, we start by probing and the pump is not activated. Then we activate the pump. And then you see that some of the pulses are going to be sent during the tension phase. Some pulses are going to be sent during the compression phase. So we are able to track the changes in wave speed as a function of strain. All right, so if we do this in a rock sample, we get a very large nonlinear elastic response. So this is the pump signal, the strain measure using an accelerometer at the top, or we can also use a laser. And so when the strain is positive, the sample is being pulled apart, and when the strain is negative, it's during the compression phase. And what we see is that as soon as we activate the pump, the velocity, so in blue here, this is the relative velocity change. So if it is 0, the velocity doesn't change. What we see is that the velocity drops on average. So the medium becomes softer, and it's oscillating with the pump. And then when we stop the excitation, it recovers, but then it takes some time to recover, and it recovers in a logarithmic fashion. So here I'm just plotting like 0.3 seconds, but it may take several minutes or several hours to go back to the initial state. So we are in a nonlinear elastic regime, but it's still elastic. In that case, we are not damaging the sample. It recovers, but you need to wait enough time. So all the contact and the micro cracks inside the rock sample have been disturbed, and then they heal over time back to their original state. Just checking the time. All right, so now what we are going to do is to look at the changes in velocity as a function of strain. And we do that for multiple amplitudes of the pump. So we first vibrate with a tiny amplitude and then with a larger and larger amplitude. And this is how we get these nonlinear signatures. So this is an example in a Riviere sandstone. And so we plot the changes in velocity as a function of strain. When the strain is positive, we are in tension. When the strain is negative, we're in compression. What we see is that as we increase the pump amplitude, the velocity drops on average. So that's related to parameter alpha coming from this hysteretic nonlinearity that I mentioned before. Then the next observation is we see, for some of the signatures, we see a slope. So we see that during the tension phase, velocity is slightly lower. So we are kind of opening all the cracks or all the grain junctions. And then during the compression phase, we are increasing the velocity. But then, especially for that particular sample at intermediate amplitudes, we see this strong curvature. So I always use this example because we get a kind of remarkable signatures for that sample. So at intermediate strain, so this is the plot on the right. This is just a zoom in of what we see here at the top. We see that velocity is actually lower in tension and also lower in compression. So when we see this, we're like, what's happening? Why is the velocity lower in compression as well? So we think that this is related to the shearing of the cracks or shearing of the grain contacts. So every time you shear in one direction, velocity is lower. You shear in the other direction, velocity is lower, and then you go through a maximum when the strain is 0. So this is our intuition of what's happening. And then we get even higher harmonics. So like at high amplitude, we get a combination of everything. So we get this kind of Mexican hat. So what we did, so this was work done in Los Alamos, actually. So we basically we do some DAT measurements for a variety of rock samples at multiple amplitude and frequency. And what we see is that when we try to find some correlation between the nonlinear parameters, we see that we have two clusters. So this suggests that there are maybe two main mechanisms behind the response that we measure. What we see is that the slope of the signature is not correlated to any other parameters. So all the other parameters are correlated with each other, except for the slope. So what we think is happening is that we have this slope beta is related to the opening and closing of the contacts. And then all the other parameters may be related to shearing of the contact. So one of those parameters is the curvature, where I told you why do we get this lower velocity when we have full compression or full tension. So we think this is coming from shearing mechanisms. So that was kind of the conclusion we were at for a few years. So now my PhD student Lingaro, she has been working on doing these kinds of measurements, but with materials of simpler composition. So rock samples, they have large nonlinear elastic properties, or the nonlinearity is very high, but the composition is also very complex. So it's hard to understand the mechanisms. So she has been using glass beads, and as well as sand samples. So the grain size is about 100 micron. And so we know the composition. One of the differences is that for glass beads, the particles are very spherical. For sand, the particles are very angular. And she also has been changing the relative humidity of the samples. So we know that the relative humidity has a strong effect. So when you have some water absorbed on the grains, it's basically pushing away the grains. So the water is like a sponge. Like water is being absorbed on the grain, and the sample is being pulled apart, and it's making the grains weaker. So we use this as a way to tweak our contacts inside the sample. So this is the experiment setup she has been using. So we have like two steel blocks, and with a pair of ultrasonic sensors at 1 megahertz inside, one to transmit, one to receive. The granular media is a few millimeter high here. And then we apply a static stress of 4 MPa. And then we oscillate 10 hertz with some superimposed like dynamic oscillations. And so this is the kind of waveform we measure on the receiver side. Okay, so she has done this with glass beads. So this is relative velocity change as a function of dynamic stress. So when the stress is positive, this is compression. So it's back one now. She's measuring the stress. So when it's positive, this is compression, and when it's negative, it's dilation. And when she changes the relative humidity in glass beads, we see that for all the dry samples, the nonlinearity is much lower than for the humid sample. So you just change the relative humidity, it's making the grain junctions much weaker, and the nonlinearity is much stronger. And when we extract the nonlinear parameters from that, we see this. So all of these are nonlinear parameters, alpha, beta, delta, related to the softening, the slope, the curvature, and so on. We see that the three parameters are increasing with relative humidity. So we see a strong effect. The problem is that all the nonlinear parameters are increasing, so it's not very helpful to try to distinguish what mechanism is what. So it doesn't really help. So she has been doing measurements in sand sample as well. Check on the term. Okay. And in that case, we see that when we change relative humidity, we don't see much change in nonlinear parameters. So what we think is happening is that because the grains are very angular in sand, when we humidify the sample, the grains are locked, the assembly is locked, and the water is not able to weaken the junction. So this is a comparison between the two. So this is kind of flat. There's some scatter and this is increasing, and this is the two together. Okay, and then one last observation that we have made is if we look at the nonlinear parameters as a function of the amplitude of the dynamic stress, we see that in glass beads on the right. So I'm looking at this parameter R2, which is related to this curvature and the shearing of the contact. In glass beads, we see that R2 is increasing with dynamic stress monotically, in a monotonic fashion. But then in sand, we see that R2 doesn't increase with stress until a certain amplitude, and then it starts to increase quite dramatically. So what we think is happening here is that the grains are locked, and if you don't shake the sample enough, then they are going to remain locked, and R2 is not going to increase. And it starts to increase only when you start to increase the amplitude of the oscillation. So this was a recent observation that we are going to try to confirm with a slightly different setup to try to reduce the scatter in the data. But this is kind of the most recent work we have been doing. So thank you.
It's really encouraging to see a great experiment that's going on here. The real experiment in rocks where you were looking at how the velocity was changing with different stress levels, you use the word healing. Do you understand physically why it actually returns back to its original state? What's going on within the substructure?
Right. So that's a good question. Yeah. So what does it mean healing? So we are disturbing the junctions. We're evaluating them. So what we think is happening, like there is a change in if you look at the microscopic level, you would see that the area of contact between two grains, for example, is decreased slightly. And it's something that has been observed in friction experiments. If you slide two surfaces and then you stop, and then you re-shear. If you stop for a short amount of time, the contacts don't have time to age, all the asperities between the two surfaces. If you wait for 1 second, then 10 seconds, 100 seconds, it's kind of a logarithmic phenomena. And so if you wait longer, then the contacts are aging. People have used an optical method to actually look at the actual area of contact between two solids. And if you wait longer, the area of contact is larger. And then when you try to re-shear, the coefficient of friction that you measure is larger the longer you wait. So we think it is kind of the same phenomena taking place between the grains, or if when you have micro cracks inside a rock sample. Yeah.
Any other questions? Okay. Well, thank you again, Jacques.
Thank you.
And let's thank all of our speakers from this morning. As I mentioned earlier, we have lunch over in Alumni Hall from 12 to 1, and then we will reconvene in this room at 1:15 for our final afternoon session. Now, is there going to be anybody in the room during lunch? Or should they take their things with them? Yeah, so there will not be anybody in here continuously. They'll be in and out. So it's up to you whether you want to leave things here or take them with you over to lunch. Yeah.